So we are going to test this series for convergence, and notice this in here. Actually, this is the same even if we start it at 2, because natural log of 1 is 0. Okay, so if we look at the series, we know this by the p-series property that the series summation 1 over n square is convergent, but we just don't have a good way of comparing the two. Okay, so let's see, by looking at various options, we arrived at the integral test. And for the integral test, what we would need is this. That is, if we make a real valued function, or if we take this real valued function, ln of x over x squared, and of course we are talking about x greater than or equal to 2, okay, then what we have is, for x greater than or equal to 2, fx is positive, okay, and fx is decreasing. An easy way to do that is this. Just go ahead and look at the derivative of f, okay, and for the derivative, what I'm doing is that I'm just going to go by plain quotient rule. So here I put the denominator, took the derivative of the numerator, okay, that is x squared times 1 over x, right? So here I'm differentiating this by using the quotient rule, and then I'm differentiating the denominator, that becomes 2x, and ln x stays as it is. And what does that become is that this reduces to x, and then we can factor an x out here. Let's do so. So 1 minus 2 ln x over x cubed. Remember, our x is greater than or equal to 2. X to the 4. And this changes to 1 minus 2 ln x over x cubed. And for x greater than or equal to 2, this quantity is less than 0, just because simply notice this. If we look at this, ln of 2, okay, look at ln, so ln of 2 is, just a moment, ln of 2 is how much? 0.6931, etc. So 1 minus 2 ln of 2 is negative. And since natural log is an increasing function, okay, what will happen is that this will be negative throughout for x greater than or equal to 2. So f prime x is negative. So what that gives us is this, that fx is a decreasing function, okay. And then for x greater than or equal to 2, this function is continuous because natural log of x is continuous for this, and the denominator is continuous and non-zero in this region. So what we have is that f is continuous on 1 infinity, right? To infinity. Actually, it is continuous on 1 infinity as well. So, but we chose to take this, so it's continuous on that. So what happens now is this, that we have that if the integral from 2 to infinity, if we can determine the nature of this integral, then the infinite series involved will have the same nature regarding the convergence or divergence. So let's just go ahead and try to determine, first let's just go for the indefinite integral version of this. So say we have to evaluate this integral. And so when we inspect it around, we see this, that is, we got ln of x over x square here. So we can do this, got this x. So let's just split that with, as a product of two x's, and then we have 1 over x dx, and 1 over x is the derivative of ln of x. So we are just going to try the substitution and see if it works. Okay, so what does du become then? Du is 1 over x dx, and since u is ln of x, we have x equals what? E to the power u. So let's just put these transform values in here. And so if we do that, what this is going to become is one moment, that this is going to become the integral, okay, ln of x is u, x is e to the u, okay, and 1 over x dx is simply du. So this is the antiderivative, u e to the negative u, okay, sorry, e to the negative u du, okay, and then if we look at this, what we have is that we will use the integration by parts here. That is, let's just bring this in. Where did my pen go? Right here. So we will do this. That is, this is u. Let's take this as dv. So what is our dv here? dv is e to the negative u du. So if we integrate, then we will be what? Negative e to the negative u. So remember this, our integration by parts, that rule tells us this, that this is uv minus integral v du. So what this will be then? We get this here then, okay, that is u times, how much is v? V is negative e to the negative u, okay, so negative u, and then minus integral v du. So v again is this, negative e times e to the negative u, and this is u, so we'll simply get a du here. Okay, so let's just go ahead and erase this portion here so that we can write further, or we have some more writing space. Okay, so this whole thing is gone. Okay, and then what we got here is negative u e to the negative u, and then plus we got again integral of e to the negative u, and what that will become is that will become negative e to the u. So we have this whole thing equal to, so here it remains the same, and then this one again would become how much? Negative e to the negative u, and I'm not taking the constant into account because we are going to look at a definite integral. So let's put this back in terms of x, and what we have here is negative u is how much? We already had it here. U is a natural log of x, right? And e to the u is x, so if we take e to the negative u, that will be x to the negative 1, so we get 1 over x here, and then minus e to the negative u again would be negative 1 over x, and then so you simply get, what do we get? 1 plus ln of x over how much? X. Okay, so this integral here, we have evaluated it already, and I'm just confirming it by computer. Yeah, we did a good job. Okay, and now what we have to do is we have to see if this integral converges, that is the integral from 2 to infinity. Okay, so let's evaluate this improper integral. And what we shall have is that first we will take the limit as x goes to infinity of this portion. So limit as x goes to infinity of this. And then we will apply the lower limit. For the lower limit, when we take x equals 2, I have minus sign. Then there will be another negative sign here. So the 2 will become positive, and this is going to become how much? Simply 1 over 2 times ln of 2 plus 1. Okay, or actually let's write it like this, that's better. Okay, that is 1 plus ln of 2, or what we wrote before was okay too. All right, now this quantity, just apply L'Hopital because infinity over infinity. So when you used indeterminate form and apply the L'Hopital's rule, what happens is this goes to 0. So simply this value will be just equal to this. Okay, and you can see that's what it is if we just distribute 1/2. So this integral, it converges. So since it converges, what happens that the series that we were looking at, we have lost it somewhere way back there, right here. Therefore, this is also convergent. Okay, now remember this, that there's one good thing with this, that is, oh actually sorry, ln n over n square converges as well. Okay, I was just copying pasting, not looking properly. Now here what it does is that, if we want to find the limit, okay, and so say for instance if we add it to say 100 terms, and you can use your sum sequence feature to do that, so you get this value. Now you want to know that what the difference between these two values would be. That is, if we look at the value of the convergent series, then we want to know what an estimate of this is, and this is a series of positive terms, so of course this will be a positive number. So you know from the remainder of the integral test criteria that this value would be what? If we stopped at the 100 term here, then that is simply this integral, right? That is ln of x over x square, and we can dx, and we can go in the same manner as we did before. Instead of 2, there we will have ln of, there we will have 100, so we can write 100 here, and 100 here, and 100 here, and what we get for that is 0.06, so 0.056 rather. So if we do this, that if we add the first 100 terms, the error, the magnitude of the error is how much? 0.056 approximately, or actually slightly more. So in here, I mean, that's an advantage that you get from this. And if and of course you saw this, that is when we were discussing it, that the convergence of this series is, pretty slow right here, 1 over n square. That's so. So anyways, here, because of introduction of this will be slower. Now, we will do this, and so let's just go ahead and determine how many terms must be added so that the error of the estimate, what do we mean by this? That this difference, okay, is less than 0.01, okay, because here it's like 0.561. So in that case, what you want to do? You want to do this, that what we should have here, okay, how much n should be taken so that this will be less than 0.01, and this is going to be which value? This is simply n. I mean, we are just doing the, I mean, it's not a general rule. Be very careful when taking such substitution. So we want this quantity to be less than 0.01. So what we would do is that we'll just employ a table from our calculator, because doing it analytically might be cumbersome, and I'm not even trying it at the moment, being so tired. Okay. So first, let's put it in a way that it's easy to put it in the calculator. Okay, so I combine these together. I'll bring the calculator up, and then I'll just change my y to 1 plus ln of, instead of n, I'm writing x here, okay, divided by x. Okay. Now we know this, that the value for y1 at 100, that didn't work because that was just too big. So actually, let's see here. We will say vars, y vars function y1, and remember the 100 didn't work. Okay, it's 0.0561 approximately. So we would do this. We'll look at several intervals and then inspect from the table. This is still too big, 0.0315. So let's go to, say, 300. Let's see what that gives us. Still big. Okay. And so, okay. So there we are just decreasing. So since I just want to go in a relaxed manner, and that's what I'm doing, and let's take a little big leap forward here. This time let's go to 800. Okay. Now here we are getting like, close to 0.01. So let's see what it would have done at 700. Okay. At 700 it is more, so the value of big N will occur between 700 and 800, right? So let's try this then. That is, I would try, say, 790, looking at the difference. Okay. So, well, it's coming up that much, so we know it's below 790. Okay, let's go 770. Okay, so it's below that even, and I'm not applying my mind at all, just going with it. So let's see. So it's between 740 and 770 somewhere. So I'm not going to do it this way. I shall just do this. Starting from 740, I'll look at the table. Okay, so here let's start at 740. And in the steps of, 1 is not too bad, that's okay. And here we go. And let's look at the table. And there we are. Let's see, okay. So right here, with the best of this calculator, we are getting it about at 760. Okay, so let's see, did we do it at 760? No, we did not. So let's see what I'm just looking at it. 760. Okay, 760. So yes, that would bring it to be less than 0.01. Actually, this value is slightly more than that. So what we may try is this, and the table didn't go that far. It was rounding up too fast. So here we get this. Okay, and so we will try and okay. So let's go farther. Okay, good. So how about trying 765 here? Okay. And 765 is enough as well. And we know 762 will be slightly more. And so I don't know why I made a big jump. Okay. So 762 appears to be, 764 appears to be our value, to the best of this calculator. Okay, so what you have is that you have to take n greater than or equal to 764 so that the error of approximation, or this value here, is, if you added 764 terms, then the value that you will be missing according to the integral test, okay, that will be no more than 0.01 as you wanted. Okay,